Hi everybody. We're going to be doing section 2.3, terminology for systems of linear equations. So we're going to begin with a definition. An m by n system of linear equations is a set of equations of the following form. A11 x1 plus A12 x2 plus A13 x3 goes all the way down until A1n xn is equal to B1. So that would be our first equation. Our second equation, A21 x1 plus A22 x2 plus, we go all the way down to A2n xn is equal to B2. So we continue that pattern, and the mth equation, there's m of them, is going to be am1 x1 plus am2 x2 plus, and then all the way down to amn xn, and that's going to equal bm. So this should look familiar to you guys. This is just a system of linear equations like you've seen in algebra. We have m equations here, right? M equations. It's also worth noting that there's n unknowns, right? The x1 through xn are your unknowns. So let's write that down. We have m equations, n unknowns. Now, for those of you that remember from algebra, you can write this system of equations in matrix form. You could take a matrix and you can write this whole thing as a matrix. In fact, you can even write it in terms of matrix multiplication. Okay. So let's go ahead and write that down. This is our matrix of coefficients. So what you can do is just write down the coefficients of the x's and put that in a matrix. And that gives you an m by n matrix. Okay, so there is our matrix. And so we can take that, so we can write that entire system on the left as a matrix times a column n vector. So this is going to be x1 all the way down to xn, and that's going to equal a column m vector of the b's. That makes sense, right? We've got an m by n times an n by 1. That's going to give you an m by 1. These two things that I've underlined are equivalent. They are just different ways of writing the same system of equations. Okay. See, that's an m by n, that's an n by 1. And the answer is an m by 1, just like we learned with matrix multiplication. And you can see that if you work this out, you get the exact same system that we got on the left. So if we write this in a compact way, this is just ax equals b. That's exactly what you're looking at on the right. We call that the vector form of the system of equations. The vector form of the system of equations. We also call it the matrix form, right? Because it's written as a matrix as well. So it's either one. You can call it a matrix or vector form of the system. Let's give these guys names because we haven't really said what they're called yet. The aij's, all of the a's that you see, those are called the system coefficients. The bj's, those are called the system constants. So all of these are numbers. The only variables here actually are the x's. So the x1 to xn, those are the unknowns. So what does it mean to have a solution to the system of equations? So let's write down what the solution means. A solution to the system is a set of scalars. Remember, scalars are real numbers. Is a set of scalars C1 through Cn such that when you substitute them, so when substituted for x1 to xn, all equations are true. In other words, when you replace the x's with those c's, the equations are all true. You guys are familiar with that. That's what it means for something to be a solution to a regular equation, right? It's the same thing for a system. So we need a definition now. What does it mean for a system to be homogeneous? An m by n system we call it homogeneous or homogeneous. It just depends on how you want to say it. I'll usually say it homogeneous. If all of the system constants, so if all the bj are 0 for all j. In other words, b1, b2, b3, all the way up to bm are all equal to 0. In other words, your system looks like this. A times x is equal to 0. Okay. So now that we know what a system of equations is, we have some natural questions that come out of this, okay? So what are some natural questions about a linear system? So first question, does a system Well, let me write this all out here. Questions about a linear system. So question 1, does a system have a solution? So that's the first question, right? Does it have a solution at all? Question 2, if yes, how many solutions are there? And question 3, how do we find all of the solutions? So that's kind of the purpose here of the next couple sections, is to build a machinery here so that we can answer all of these questions for any system. So we have a definition here that we need. The solution set, you've probably heard these words before. I know when I teach algebra, we use words like solution set. So the solution set of a system is just the set of all solutions. So you may wonder, does a system of equations have a geometric interpretation? So the answer is, if you have a 2x2 system or a 3x3 system, yes, there are geometric interpretations that you can make about the system. Of course, anything beyond 3 variables, you're no longer in 3 dimensions, so we cannot visualize it. So let's talk about the 3x3 case. So what is the 3x3 visual example that you should keep in mind? Let's first write down what a 3x3 generic system looks like, okay? We've got a11x1 plus a12x2 plus a13x3 is equal to b1. a21x1 plus a22x2 plus a23x3 is equal to b2. And a31x1 plus a32x2 plus a33x3 is equal to b3. Okay, so this is a 3x3 system of equations. And for those of you that remember your Calc 3, your multivariable calculus, aren't each of these equations a plane? So really, we have 3 planes here, and we want to know a solution here is going to be something that intersects all 3 planes. So the question is, what are the possibilities here of what can happen? How can 3 planes intersect in space? There are, in fact, 4 possibilities. So let's write down what the possibilities are. The first possibility is that the planes don't intersect at all. This is possible, right? All 3 planes could be parallel. So what does this mean if they don't intersect? How many solutions do we have? We have no solutions. And so we have a name for this. This is called an inconsistent system. In other words, the equations don't agree with each other, right? They don't meet anywhere. They're inconsistent. What's the second possibility? the planes intersect in exactly one point. So if they intersect in one point, then that means that they have one solution, right? One solution. Okay. What would the third possibility be? The third possibility is that the planes intersect at a line. So if they intersect on a line, then that would be an infinite number of solutions, right? Infinite number of solutions. Is that the last thing that can happen? No, there is a fourth possibility, which is that all the planes are identical. If all the planes are identical, by the way, then that means that the planes intersect on a plane, don't they? This, of course, also has infinite solutions. It's worth noting that even though the last two cases here are infinite solutions, we do view them differently, right? A line is different than a plane, so we will distinguish between those in this class later on. So all three of these are considered consistent systems, because if you have at least one solution, the system is consistent. All right, so these are the four possibilities for a 3x3 system. So let's talk a bit more about how you use matrices to represent a system. We call the system, we call the matrix of all of the A's, we call that the matrix of coefficients. So let's just write that down. Sorry, that should say AMN. So this is our matrix of coefficients. So that's just the coefficients, but normally what we want to do is we want to write all of the coefficients, but we're missing the b's. The b's are important, right? Those are the constants that go on the other side. So for this, we have something called the augmented matrix. The augmented matrix. So that's when you put all of the A's and then we put a line, and then we put all of the B's. You could put a solid line or a dotted line, but we have a line and then all of the B's. I'll make it solid so you could tell the difference here, okay? So if you add in those B's, we call that the augmented matrix. This will completely tell you the system of equations, right? So what we've done is we've taken A and we've adjoined or augmented it with B, right? let's think about the size of this matrix, right? If A is an m by n matrix, this guy is an m by n plus 1 matrix, because now we have n plus 1 columns. See, this one over here was an m by n matrix. So what we have here, the guy on the right, represents the system of equations. We're going to be using the notation on the right quite a bit in order to solve systems of equations in the following sections. Now, what about the names of these things? Or we want to use symbols. So I'll explain the symbols in a moment. Let's go ahead and do an example here. We're going to write the following as a system. Yeah, so let me go ahead and write down the symbol that we use, okay? So if the original matrix was A, then we call this guy, you can call it the augmented A, but I call it A sharp, just because the little pound symbol up there, I'm a music guy. So I think calling it A sharp is just an easy way to say it. Okay, so A sharp would be the matrix A along with the B's attached to it. So let's practice writing an augmented matrix A sharp as a system of equations, just so we see how it works. So let's start with this matrix, -2, 4, -7, 0, -1, 6, 5, 2, 0, -1, 2, 4, and then we've got the B's are 6, -2, 8. So this corresponds to a system of equations. So let's write it in equation form. So how would we do that? How many unknowns are there? Well, there are 4 columns to the left of the line, so each of these corresponds to the coefficients of the corresponding x's that I'm writing. So we've got x1, x2, x3, and x4, and the ones on the right are the constants. So then let's write down what the equations would be. The first equation would be -2x1. There are no x2s, so we could skip that. So plus 5x3 minus x4 is equal to 6. That's your first equation. Then we've got 4x1 minus x2 plus 2x3 plus 2x4 equals -2. Then we've got -7x1 plus 6x2 plus 4x4 is equal to 8. All right, so we can always go back and forth with this notation. We can go from augmented to system or system to augmented matrix. So let's write down the vector form again, ax equals b, and I want to remind you guys of where all these objects live. Since A is an m by n matrix, it lives in the following space, right? That is the set of m by n matrices whose entries are real numbers. That's what that notation means. So these are, remember, an n column vector that just lives in Rn. And the b's are the m column vector, or column m vector, so that lives in Rm. So because the solution are part of Rn, let's go ahead and write down the formal set definition of a solution set. We call this set builder notation. So it's the set of all vectors in Rn such that they solve the system. This is, of course, a subset of Rn. Okay. I will always be introducing this type of notation to you guys just so you have an idea of how to write it formally. So let's go with our example here. We don't know how to solve a system of equations yet, but we want to show that something is a solution. So for this example, let's show for all a, b, and r, in other words, show for all real numbers a and b, the following general vector solves the system. First component, 24 plus 5a minus 10b. Second component, negative 8 minus 4a plus 3b. Then a, and then b. So show that that solves the following system. x1 plus 2x2 plus 3x3 plus 4x4 equals 8. And 2x1 plus 5x2 plus 10x3 plus 5x4 equals 8. So all we need to do to check that that thing up there is a solution is we need to substitute those things into both equations and show that they are both true. So this guy would be x1, this guy would be x2, a would be x3, and b would be x4. So we're going to substitute all of those in for equation 1, see if it's true, and then for equation 2, see if that's true. So we're going to start with equation 1. So I'm replacing x1 now with 24 plus 5a minus 10b. So I'm rewriting equation 1 with all of those things up there substituted in. So we've got 24 plus 5a minus 10b minus, so now what? We have to double x2, right? So plus 2 times x2, so that's going to be minus 16 minus 8a plus 6b. And now we need to write plus 3 times x3, so that's plus 3a. And then plus 4 times x4, so that's plus 4b. We want to know if that equals 8, right? That's equation 1. We need to see if that actually works. So let's combine all the like terms on the left and see what we get. So we've got a 24 and a minus 16. That gives us 8. Now let's look at the a terms. We've got 5a We've got negative 8a, that's negative 3a, plus 3a gives you 0, right? So the a's are gone. And now let's look at the b's. We've got negative 10b plus 6b, that's negative 4b, plus 4b, that equals 0. So we get 8 equals 8. So equation 1 works. It is a solution. So now we're going to check equation 2. So let's go ahead and plug it in. We have to double x1, so that would be 48 plus 10a minus 20b. And then we have to add 5 times x2, so that's going to be minus 40 minus 20a plus 15b. And then we have to add 10 times x3, that would be 10a. And then plus 5 times x4, that would be plus 5b. So does that equal 8? (48 minus 40 is 8. Combine all the like terms here. So let's do the a's now. Positive 10a, negative 20a. That gives us negative 10a. Plus 10a gives you 0. And then for the b's, negative 20b plus 15b is negative 5b plus 5b gives you 0. So again, we have an 8 on the left and an 8 on the right. The equation is true as well. So that proves that that vector up there is a solution. That guy is a solution. Now, one important thing about system notation is that we can also formulate differential equations in a similar way. In particular, systems of differential equations. Can be formulated using matrix functions also. So this is what it looks like. When you do a differential equation using matrices, it looks like this. X prime of t equals a of t times x of t plus b of t. This is what the matrix form of a system of differential equations looks like. Or the vector form, either way, right? We've got a matrix and a vector in here. This comes way later in the course, but we are going to demonstrate a quick example right now, just to check that something is a solution. So let's write down a system. I just wanted to add this vector form part here because we don't just call it matrix form, it's a vector form as well. So let's look at this example. This will be our last example. So consider the following system of differential equations. So the first differential equation is x1 prime of t is equal to 2x1 of t minus x2 of t. So here we have two unknown functions, right? x1 of t and x2 of t. And the second equation is x2 prime of t equals negative 2x1 of t plus 3x2 of t. So these are our two equations. This is a system of differential equations. We have two unknown functions and two equations. So first thing we want to do is to write it in vector form. So let's start by taking our two x1 and x2 of t functions and writing that as well, let's start with writing the matrix, right? Yeah, we've got, sorry, I wrote that wrong. I need to write my, my vector first. Yeah, so, okay. We have an x1 of t and an x2 of t. We've got that vector on the left is equal to the matrix times that vector on the right. That's how you write it. And so if you were to let A be the matrix of coefficients 2, -2, -1, 3, and you were to let X be x1 of t, x2 of t, column vector, then that means our system is really x prime of t is equal to a of t times x of t. There you go. We've got our vector form of our system of differential equations. So that's just part A. For part B, we're going to do something a little bit different. So for part B, we're actually going to verify that a particular vector is a solution to the differential equations. So of course we have two unknown functions, so I have to give you two functions as a solution. So those are my two functions. Verify that e to the 4t comma -2e to the 4t is a solution to the system. So how do we check that that is a solution? Remember, we have to take the derivative. It's a differential equation, right? The derivative appears in there, so we need to replace the functions and also the derivatives into the system. Okay. So there's my x vector. Let's go ahead and take our derivative of our x vector. Taking our derivative, using the chain rule 2 times, we have 4e to the 4t on the top, and negative 8e to the 4t on the bottom, right? That's our derivative. Pretty simple to take. So we've got all of that, and now what we're going to do is we're going to replace each equation in the differential equations and make sure that they're each true. So remember, that's our x1, that's our x2. x1 prime is 4e to the 4t. x2 prime is negative 8e to the 4t. So let's go ahead and try in both equations. We're going to start with equation 1. So equation 1, remember, is this guy, and equation 2 is this guy. So let's start with equation 1. We want to do x1 prime of t. We want to write that on the left of the equal sign. That's going to be 4e to the 4t on the left of the equal sign is equal to 2. Well, we don't know if it's equal yet. That's what we're trying to see. So it's equal to 2e to the 4t. Remember, we're doing minus x2. So that's going to be minus a negative. So that gives us a plus. So it's going to become plus 2e to the 4t. Are those equal? Yes, because 2e to the 4t plus 2e to the 4t is 4e to the 4t because they're like terms. Okay, so equation 1 is true. Now let's try equation 2. Remember, that equation was x2 prime of t, so we're going to write negative 8e to the 4t equals, and then we have to multiply negative 2 times the first function, so that's negative 2e to the 4t. And then plus 3 times the second function. That would be minus 6e to the 4t. Combine like terms on the right side. Negative 2e to the 4t minus 6e to the 4t is negative 8e to the 4t. We've got a negative 8e to the 4t on both sides, so yes, it is true. Therefore, it does solve the differential equation. You can write it as a column 2 vector like this, or you can write it as a horizontal regular vector on the top, right? Like the problem gave us. Either way is fine. So this is a solution to the system. All right, everybody, so that's it for this lesson. Again, we don't know how to solve these systems yet, but we will be learning them in the future lessons. Thank you so much for watching, everybody.